All right, so the next video, we're just going to talk a little bit. We're not going to do any problems, but we will talk about linear air resistance. And then after that, we'll do the questions associated with 2.2. Okay, so linear air resistance. I drew this little free body diagram over here of this ball or whatever you want it to be, moving at a speed v, and the forces acting on it are the weight force, which is just mg, and then we're saying linear air resistance. And then over here, I wrote the Newton's laws of motion. So mass times our second derivative of position is mg minus bv. Now, we can simplify that a little bit to be mv dot, so first derivative of velocity, is mg minus bv. And this is a first order differential equation because the highest derivative we have is our first derivative, velocity. And the really cool thing about this is we can break it up a little bit. We can say mass times velocity in the x direction is just going to be, well, the way we'll set it up, minus bvx. And mass times the first derivative of velocity in the y direction is going to be mg minus bvy. Okay? So the cool thing about this is you can break it up into its x and y components pretty easily and work through it. So let's look at an example of horizontal motion with linear drag. So this might be a cart moving on a track back and forth. So if we were to draw a free body diagram, the only net force that we're interested in, is right here. The linear force, which is minus bv. And just to set up a few initial conditions, we'll say that our initial position at time 0 is 0, and our initial velocity is just vx naught. Okay? So, doing this, we can write this as velocity. The first derivative of velocity in the x direction is minus k vx. Okay, so let me address some of this. K is just b over m. So the b was the coefficient with drag, and m is when we divide over. So that's all that is. Now, once again, this is a first order differential equation because, again, it's just a first derivative. Now, how do we solve this? There's different ways to solve different differential equations, but in terms of this, the easiest way is to recognize that this is in the form f prime of x is equal to some constant times f of x. Okay? So the derivative of velocity is equal to a constant times velocity. Well, there's only one function we know of that if you take its derivative, you just get itself times potentially a constant. And that's where f of x is equal to a constant e to the minus kt. Okay? Now we can check this. That's a cool thing about differential equations is you can always check your answers. We're saying our velocity in the x direction is some constant a times e to the minus kt. And if we take the first time derivative of that, we'll just get minus a k e to the minus kt by chain rule. So maybe review that. And if we look at our equation, we're saying f dot of x, so this is equal to minus k times v of x, which we said was just a e to the minus kt. Well, these are equal. This is a true statement. The a's, all this stuff cancels. Sorry about this screaming. So yeah, that differential equation works. I have someone's flying in, so the house is kind of chaotic right now, and there's also my little brother, but I think the points will still be made. Okay, so we just showed that that was, in fact, the solution to the differential equation. And we know that our velocity in the x direction that's when time is equal to 0, is just Vx naught. So when this is Vx naught is equal to AE to the 0, because it's minus k times t, which is 0. So we find that A, this constant, is just our initial velocity in the x direction. So putting it all together, Vx is Vx naught e to the minus kt. Okay? Or I'm going to write it a different way. Vx naught e to the minus t over tau, where tau is 1 over k, which is your mass over our coefficient. So I'm just introducing some different notations and some different ways of writing this stuff down. Hopefully it doesn't confuse us too much. Okay. Graphically, what this looks like, if we can imagine, is, let's say this is velocity in the x direction, this is time. Let's do a different color for that, actually. Let's say this is Vx naught, so our initial velocity at time 0. Our graph will start to slow down, right? That's what our graph looks like. So the big thing here is that if we look at our exponential graph, it's going to decay. And that makes sense if you think of a cart moving. Conceptually it makes sense, where if you push a cart and it's experiencing air resistance, it's going to slow down. And that's what we're seeing here, that the limit as t goes to infinity of our function is equal to 0. So conceptually that makes sense. Limits are really good, particularly if you're looking at extreme cases like initial velocity at time equals infinity. You can see if it conceptually makes sense, and this definitely does. Okay, so what about finding x of t? So this is the big thing in mechanics a lot, is you want to find position. Well, we know velocity is the derivative of position. So Vx dt is equal to dx. And if we do some integration here, what do we get? Well, let's do the easy side first, the dx. This will be x from x naught, which is equal to 0 by our initial condition, to x, which is just x of t. So that's this side. Now, what's that equal to? Well, what we have is we have the integral from 0 to t of velocity, which we know. We said that was v naught in the x direction times e to the negative t over tau dt. And if x naught, by the way, if this wasn't equal to 0, what we would have to do is add over x naught. But it's 0, so there's not really a need to do that. Okay, so integrating this, hopefully you guys are okay with this. This is a chain rule. That'll be minus v naught. It's backwards of the chain rule with e. So hopefully you guys are okay with that. Our tau comes out, e to the minus t over tau, evaluated from 0 to t. So this is equal to minus v naught x tau e to the minus t over tau, minus a negative, so plus v naught x tau. E to the 0 is just 1, so that's all we're left with. So x as a function of time is v naught x tau. So I'm factoring the v naught x tau out of each one, and I'm left with 1 minus e to the minus t over tau. And just writing it a little bit differently, we can say this is x to infinity times 1 minus e to the minus t over tau, where x subset infinity is just v naught tau. And graphically, if we were to imagine that, the reason why I did that notation is because I think graphically it'll help us understand it better. Let's say this is x and this is time. What does our graph look like? Well, it's going to look something like this. And it's going to kind of eventually asymptotically approach what we're saying is x sub infinity. So in other words, the limit as t goes to infinity of x sub t is going to be this x sub infinity, which we said was our initial velocity times tau. So then tau might be, some time over here. So hopefully that part makes sense. Now let's consider vertical motion with linear drag. Okay, so just a quick free body diagram. Our weight force, which is just mg, and then we can have our drag force right here. So that's what our free body diagram looks like. And we use Newton's laws of motion. We're only interested in the y component. So that's mg minus bv. And let's just make a note that when this is equal to 0, v sub y is v terminal. So I'll go ahead and define terminal velocity because that's an important part. Terminal velocity. So v terminal, which is our terminal velocity, is equal to mg divided by b for linear drag. And these, important to note, are a constant. So v terminal is really a constant, which is going to be really helpful when we go to work through these. Okay, so mv dot y is equal to, so I'm going to write this maybe a little funny, but I think it'll make sense after I explain it. V terminal times b minus b velocity in the y direction, or another way of seeing this is mvy dot is equal to minus b times vy minus v terminal. So hopefully you guys see that I just substituted v terminal into our Newton's laws of motion over here. So mg over b, I just replaced that with v terminal. So if we do that, hopefully you see the substitution, I didn't change anything and you're okay with why that's all right. And then the next step, I just factored it out. So this is, once again, a first order differential equation. Now the way that I'm going to solve this differential equation is I'm going to let u be our vy minus v terminal. And obviously, if I do u dot, remember v terminal is a constant, so it would be just the derivative of velocity. Okay, so what do we have here? We're dealing with the exact same situation we had before, where we have a function, right? And that's going to be included with, we have a derivative equal to something times its function. So that was the exponential case. That's the only function where that works, just like before. And we know, well, what I'm saying is that our initial velocity is just going to be vy. So if we set these equal to each other, we have vy minus v terminal, this bit, is equal to u, which is a e to the minus t over tau, where t, this is 0. Right? So A equals, I'm sorry, U, that's this part. I'm sorry, no, A, we want A. A equals Vy minus V terminal. So this part is going to be equal because this is just going to be 1. Okay, so we know that. So now that we are okay with that bit, we can say Vy minus V terminal is equal to A, Vy minus V terminal, times e to the minus t over tau. So using our initial conditions, we are able to solve for A. And finally, we can say Vy is equal to V terminal plus Vy minus V terminal e to the minus t over tau. So all I did was I added that bit over. And now what I'm going to do is V sub y is equal to. So I'm going to try to simplify this just a little bit. So we'll have V sub y e to the minus t over tau plus V terminal. I'm going to factor the V terminal out from each of these, and you'll get 1 minus e to the minus t over tau. Maybe I did that a little quick. What I did was I just distributed, right? And this term is right here. And then I looked at these two terms, and I just factored out the V terminal, and I'm left with 1 from here times our e from over here. So hopefully I didn't go too fast there, but that's all that was done. Okay, so graphically, it's a big graph, it's fine. Let's say that this is V and this is T. Maybe this is tau. Maybe this is 2 tau. Maybe here's 3 tau. And the important thing to see is this is V terminal, and we're approaching this terminal velocity. Another way to think of it with calculus is the limit as t goes to infinity of our velocity function is going to be equal to V terminal. So when our force is balanced and we no longer have any acceleration, there's no slope to our graph, we're approaching terminal velocity. Okay, so let's make a note of what happens when t equals tau. That's equal to V terminal times 1 minus e to the negative 1, which is about 0.63 V terminal. In other words, when time is equal to this tau, which we defined up above, I think we actually did it at the beginning, but you're about 63% of your terminal velocity. So if we make a little chart here, time t in percent of V terminal, we could be at 0, tau, 2 tau, 3 tau. And you can plug these numbers in. What you'll get is 0, 63%, 86%, and 95% are terminal velocity. So we're gradually getting closer and closer to being VT, and it's okay to approximate. For example, you might be okay saying, hey, at 3 tau you've approached, for all intents purposes, your terminal velocity. Okay, cool. One last thing we want to do is find our position function. Well, we found our velocity function. That was V terminal plus V sub y minus V terminal e to the minus t over tau. All we have to do is integrate both sides. Y as a function of t is equal to V terminal, the integral from 0 to t, dt plus Vy minus V terminal, the integral from 0 to t e to minus t over tau dt. So I just split this up into two separate integrals and factored out my constants. Y of t is just V terminal t plus Vy minus V terminal times minus tau e to the minus t over tau evaluated from 0 to t. So if we were to go ahead and do the second part of the fundamental theorem of calculus and evaluate that, which we'll do here. Let's see. We get minus tau e to the minus t over tau plus just tau, because e to the 0 is 1, and it's f of b minus f of a, so the negative turns into a positive. And then just simplifying this just a little bit, you get V terminal times time plus Vy minus V terminal. I'm going to factor out a positive tau, and I'm left with 1 minus e to the minus t over tau. And there you go. That's our position as a function of time. So we started off with, we went on a few tangents here talking about different things, but essentially with both horizontal and vertical drag, we start off with Newton's laws of motion. We simplify it to a first order differential equation. We solve the differential equation, and then after you solve it, which in this case they were kind of simple, there's different ways of solving them. They won't always be this way, but one way is just to recognize that. It's something to be on the lookout for. We graphed our functions, or velocity and position functions, and we solved for position. So after this, we'll start working